Hello everyone, I am Vimukti Nimalsiri and I will be presenting our research on the CXL-Sec dataset chest X-ray with lung segmentation. This research was conducted by Mahela Hennayaka, Kasun Ratnayaka, Dr. Tanuja Ambegoda, Professor Dulani Meedeniya and myself. I will start off with a brief introduction about the domain of our research. Lung diseases are a major cause of death around the world and medical professionals use X-ray images to detect various anomalies in lung area. There are a lot of studies on automating the process of detecting anomalies in lung area using machine learning techniques. For those studies, using segmenting images can help to ensure that model focus on the lung area instead of the shortcuts such as the image background and hospital tokens. There are a number of datasets available with chest X-ray images, but only countable number of datasets available with segmented chest X-ray images. Also, when it comes to medical image report generation for model training, segmented datasets with medical reports are rare to find. As a solution for these identified issues in the domain, we are introducing CXL-Sec dataset, which is a chest X-ray dataset with lung segmentation. Also, more importantly, with medical reports for each image. So from this paper, we are proposing a chest X-ray dataset with lung segmentation which includes total of 243,334 frontal images of both antero-posterior and postero-anterior views. On the process of creating this dataset, we did comparison of performance of different unit models on chest X-ray image segmentation and a comparison of classification result using Mimic CXR dataset and CXL-Sec dataset, which is the proposed dataset using different CNN models. Later in the presentation, we will discuss about those comparison results. So now let's check on few of the existing chest X-ray datasets. One of the popular chest X-ray datasets is the Shenzhen Hospital dataset from China. They captured X-rays in 2012 using Philips DR digital diagnostic system. These images are in PNG format and patients' abnormalities are mentioned in a separate text file. Another similar kind of dataset was introduced with the help of Department of Health and Human Services in USA. However, it consists of only 138 CXR frontal images. The images in these datasets are captured using Eureka stationary X-ray machine. A text file is associated with this dataset including the patient's details such as gender, age and lung condition. The specialty in this dataset is that they have made available the manual lung segmentations used for their lung segmentation algorithm. These images have larger lungs compared to the Shenzhen dataset. Another popular dataset for segmentation task is the Japanese Society of Radiological Technology dataset, which we normally call as JSRT dataset. It was created in 1998. JSRT is also facilitated with the text file mentioning the patient's abnormality. V7 Labs COVID-19 X-ray dataset is another widely used dataset for chest X-ray segmentation tasks. Masks of the corresponding CXR images are also provided with this dataset. This dataset consists of 1,602 normal images, 4,250 pneumonia images, and 439 COVID-19 images. This dataset also contains frontal and lateral X-rays, but masks were not provided for lateral X-rays. Also, Leaching have published CXR segmentation images from the Mimic CXR dataset. They have used Turner's Net, which is a unit architecture based segmentation model, to segment the images in the Mimic CXR dataset to create this new dataset. For this study, they have used randomly selected 4091 CXRs from the Mimic CXR dataset. After eliminating false recognitions by human examination, they produced only 1141 segmented lung images. Let's now move into the methodology of our study. Here you can see the primary workflow which we use to segment the images of the Mimic CXR dataset. First of all, we have done a comparative analysis of different unit variants to find out the best possible model for chest X-ray segmentation. Here we have used 4 different segmentation models, namely UNet, UNet++, Attention Unit and SA Unit, which uses spatial attention mechanism. We have selected Attention Unit and SA Unit models since the attention mechanism is quite popular and gives state-of-the-art performance these days. After the analysis, we have found that SA Unit has outperformed all the other models. Thus, we have used SA Unit to do the segment the images of Mimic CXR dataset. We have generated masks for all the frontal images of the dataset and further performed morphological dilation and erosion to remove any blank spots and holes in the masks. Finally, the segmented images for the corresponding mask is obtained by a bitwise operation and saved both mask and segmented image on the same location in JPEG format. This table shows the data augmentation that we did to obtain a comparatively larger dataset to train the segmentation models. Since the Mimic CXR dataset is a larger dataset, it is better to train the segmentation model with a larger chest X-ray dataset to achieve better results. However, most of the chest X-ray datasets, which include masks, do not contain many images. Because of that, we have used a combination of 3 datasets to train the SA-unit model, namely Shenzhen Hospital dataset, Montgomery County dataset, and V7 Labs COVID-19 dataset. Furthermore, data augmentation is used to reduce the class imbalance of the combined dataset. Also, data augmentation is performed in a way that it reduces the class bias of the combined dataset. Moving forward, these are the data preprocessing methods which were applied to the input dataset before proceeding with this training. Both images and masks were resized to 224 x 224. Then, contrast-limited adaptive histogram equalization was applied to images to improve the contrast of the chest X-ray images. This method applies histogram equalization in small tiles with contrast limiting. As the final preprocessing step, both images and masks were normalized to a range of 0 to 1. Image normalization adjusts the values of the data to a common scale without changing the range. Having a similar data distribution makes convergence faster while training the network. Also, we have chosen traditional data augmentation methods like flipping, rotating, cropping, scaling, and zooming. For the training, the dataset was split into 80 to 1010 train test validate ratio and trained for 15 epochs. Adam optimizer with a learning rate of 1 into 10 to the power of minus 4 was used with a batch size of 5. For the loss function, we have used a combination of dice loss and cross entropy loss. Here shows the workflow diagram of the whole process. Trained model weights were saved after and retrieved when we needed to do the segmentation of Mimic CXR dataset. The generated mask and corresponding segmented images were saved in a similar folder structure as the original dataset to increase the usability. Next, we will have a small look on the SA-unit architecture which we used in our study. In the field of medical image segmentation, UNIT is a common and well-known backbone network. Basically, UNIT consists of a typical downsampling encoder and an upsampling decoder structure and a skip connection between them. It combines local and global context information through the encoding and decoding process. Due to the excellent performance of UNIT, many recent methods for chest X-ray segmentation are based on UNIT. Although these UNIT variants performs well, they inevitably make the network more complex and less interpretable. In order to address these problems, SA-unit model introduces a unit with a spatial attention mechanism, which is a lightweight network model. Specially, SA-unit uses a structured set of dropout layers which they called a drop block that can effectively prevent overfitting of the network. So even small sample datasets can be well trained. In addition, batch normalizations can improve the conversion speed of the network. Figure on the left shows the SA-unit with a U-shaped encoder on the left and a decoder on the right side of the structure. Every step of the encoder includes a structured dropout convolutional block and a 2x2 max pooling operation. The convolutional layer of each convolutional block is followed by a drop block, a batch normalization layer, and a rectified linear unit. And then the max pooling operation is utilized for downsampling with a stride size of 2. In each downsampling step, they double the number of feature channels. Each step in the decoder includes a 2x2 transposed convolutional operation for upsampling and halves the number of feature channels and concatenates with the corresponding feature map from the encoder, which is then followed by a structured dropout convolutional block. The spatial attention module is added between the encoder and the decoder. At the final layer, a 1x1 convolutional and sigmoid activation function is used to get the output segmentation map. Drop block, a structured form of dropout, can effectively prevent overfitting problems in convolutional networks. Its primary difference from dropout is that it discards contiguous areas from a feature map of a layer instead of dropping independent random units. Based on this, SA-unit has a structured dropout convolutional block. That is, each convolutional layer is followed by a drop block, a layer of batch normalization, and a ReLU activation unit, as shown in the figure on the right. Finally, the spatial attention mechanism was introduced as a part of convolutional block attention module for classification and detection. SA uses the spatial relationship between features to produce a spatial attention map. This is the main dataset that we use to create our CXL-Seg dataset. Actually, our work is an extended version of the Mimic CXR dataset. Before going to the details of the CXL-Seg dataset, first let's get an idea about the Mimic CXR dataset. The Mimic Chest X-ray is a publicly available dataset for deep learning tasks related to image classification and report generation. It contains 377,110 chest X-ray images and 227,827 corresponding studies. Each study consists of frontal and lateral view X-ray images of the chest. The Mimic CXR dataset is available in two versions. One of them is Mimic CXR DCOM version. This version uses the digital imaging and communications in medicine, which is the DCOM format, which stores multiple images in a single file along with metadata in the header. In the Mimic CXR dataset, the metadata includes view position, patient orientation, and anonymized data of image acquisition time, allowing for chronological ordering of the images. The whole dataset is approximately 4.6 terabyte in size. Since this DCOM version is too large in size, Mimic CXR is available in JPG format as well. This is a compressed version of the dataset that uses the images from the DCOM files in the original Mimic CXR dataset. It is intended to provide a more convenient version of the dataset for researchers since the size of this dataset is approximately 557 gigabytes. Each study in the dataset includes a report with an examination, indication, technique, findings, and impression for each chest X-ray images, as well as metadata for each image in a separate CSV file. Also, the dataset is coming with a split CSV which split this dataset into test, train, and validation dataset to the ratio 97.8 to 1.4 to 0.81. Another interesting fact is each study is classified into 14 classes using the Checkspert labeler, and those classes are also included in the metadata CSV file. These are few sample images and relevant reports from the Mimic CXR dataset. Now let's dive into the details of the CXLSec dataset. Since this is an extended version of the Mimic CXR dataset, folder structure is almost same as the original dataset. All the lateral views of the chest X-ray images are removed since we did the lung segmentations. Also, we were able to find that 10 studies were missing medical reports through a systematic sanity check. Because of that, we removed those frontal images from our dataset as well. The segmented images and the relevant mask is stored in each study folder. Also, images are in JPEG format and the whole dataset is only 4.24 GB, which includes 224x224 segmented images and masks. We have also updated the CSV files as well to make the dataset more convenient to user for research. Also, we have changed the train test validation split ratio to 80 to 1010 and added a new CSV file that includes the mapping between the original image and masks. Here are few sample images from our dataset, and since we are providing the mask with the dataset, anyone can use these datasets to train their own segmentation model as well. Let's now look at the results of our study. Here are the results of the comparative analysis that we have performed to identify the best performing segmentation model out of the selected 4 unit variants. As we can see, SA-UNet achieved the highest scores of Dice coefficient, intersection over union, recall, and precision. And it also has the minimum score for the loss as well. Moving forward, here we can see the training or validation curves for the accuracy and loss of selected unit models. Clearly, SA-UNet model shows a high level of convergence than the other models. Apart from that, UNet++ and Attention UNet models also show a decent amount of convergence. On the other hand, UNet shows a small divergence towards the end of the curves, which means the model has overfitting issues. Thus, considering all those, we have selected SA-UNet model to do the segmentation of the Mimic CXR dataset. Moving forward, to measure the performance of the CXLSec dataset, we have done a classification task from the two datasets, Mimic CXR dataset and CXLSec dataset. Here we have used the same split ratio and the same conditions to do the classification task. We have used 4 CNN models to do the study, namely ResNet 50, MobileNet V2, DenseNet 121 and Inception V3. In all 4 models, we have got better results using the CXLSec dataset, and it proves that this dataset can be used to enhance the results of the existing models to achieve better results rather than using the original dataset directly. To conclude, we tried with several unit models and found out that SA-UNet performs the best for segmentation. It was able to achieve 96.8% of Dice coefficient and 91.97 intersection over union score. Because of this higher accuracy during segmentation, CXLSec dataset can be used for chest X-ray classification tasks, report generation tasks, and to train segmentation models as well. That's all about our presentation. Thank you.